sklearn Ensemble Gradient Boosting Classifier. Description: Gradient Boosting Classifier is an ensemble method in scikit-learn that combines multiple decision trees to create a strong predictive model. It works by sequentially adding trees, each focusing on correcting the errors made by the previous trees. This iterative process gradually improves the model's accuracy. Inputs: X feature matrix containing the independent variables. Each row represents a sample, and each column represents a feature. Y target vector containing the dependent variable. This vector should be of the same length as the number of rows in the feature matrix. Outputs: Model a trained gradient boosting classifier object. This object can be used to predict class labels for new data. Predictions: the predicted class labels for the input data. Steps: Initialization: the first tree is trained on the entire dataset. Iterative training: in each iteration, a new decision tree is trained to predict the residuals errors of the previous model. Weighted aggregation: the predictions of all the individual trees are weighted and combined to produce the final prediction. Metrics: Accuracy: the proportion of correctly classified samples. Precision: the proportion of true positives among all predicted positives. Recall: the proportion of true positives among all actual positives. F1 score: a harmonic mean of precision and recall. AUC: area under the curve, the area under the receiver operating characteristic ROC curve, which measures the model's ability to distinguish between different classes. Visualization plots. Feature importance plot visualizes the relative importance of each feature in the model. Decision tree plots visualizes the structure of individual decision trees in the ensemble. ROC curve plots the true positive rate against the false positive rate for different classification thresholds. Precision recall curve plots precision against recall for different classification thresholds. Fine-tune parameters. Nestimators: the number of decision trees in the ensemble. Increasing this value can improve accuracy but may increase training time. Learning rate: the contribution of each tree to the final prediction. Smaller values can lead to smoother decision boundaries but may require more trees for convergence. Max depth: the maximum depth of each decision tree. Smaller values can prevent overfitting but may reduce accuracy. Min-samples split: the minimum number of samples required to split a node. Larger values can prevent overfitting but may reduce accuracy. Min-samples leaf: the minimum number of samples required to be at a leaf node. Larger values can prevent overfitting but may reduce accuracy. Subsample: the fraction of samples used for training each tree. Values less than 1 can reduce overfitting and improve generalization. Uncertainty methods. Confidence intervals: calculate confidence intervals for the predicted probabilities. Out-of-bag predictions: use the predictions from trees that were not used to train a specific sample to estimate uncertainty. Challenges and fixes. Challenge 1: overfitting. Sample use case that resulted in challenge 1: when the model is trained on a small dataset or with a large number of features. It may learn the training data too well and fail to generalize to unseen data. Fixes to challenge 1. Reduce the number of features. Use regularization techniques, such as L1 or L2 regularization. Use early stopping to prevent the model from overfitting the training data. Increase the minimum number of samples required to split a node. Min-samples split and the minimum number of samples required to be at a leaf node. Min-samples leaf. Challenge 2: high training time. Sample use case that resulted in challenge 2: when the dataset is very large or the number of trees in the ensemble is high. Training the model can take a significant amount of time. Fixes to challenge 2. Reduce the number of trees in the ensemble. Nestimators. Use a smaller learning rate. Use a smaller maximum depth for the tree's max depth. Use a smaller subsample fraction. Use a parallel processing library, such as Dask or Joblib, to speed up training. Use a GPU for training, if available. Challenge 3 interpretability. Sample use case that resulted in Challenge 3 gradient boosting classifier can be difficult to interpret due to the complex nature of the ensemble. Fixes to Challenge 3. Use feature importance plots to identify the most important features. Use partial dependence plots to visualize the relationship between a specific feature and the predicted outcome. Use SHAP's happily additive explanations to explain the contribution of each feature to the prediction for a specific sample.